So, greetings, I'm Catherine Pfaff. I'm a math professor at Queen's University in Kingston, Ontario. So, that's me. And I wanted to talk about, so this is a continuation of Functions Bootcamp. As we've been talking about, this is something that I often do at Queen's University to kind of get students more familiar with functions. And I want to talk about injective, surjective, and bijective functions. There's a lot more actually in the notes that are kind of in the comments, so I recommend that you look at those. But I will cover the definitions and some examples, and then I think there's more examples and proofs and so on. So I would recommend looking at that. Great. So suppose that, without further ado, so we start out with one, definitions of all these things. Okay, so suppose that f from s to t is a function. Okay, then by definition, so this is how this is going to work. So definition 1, so we're going to suppose this throughout this section. So definition 1 is going to be for an injective function. Okay, so we say that f is injective or one-to-one. So f is injective, so this is one word for it. The other word, it means we're talking about exactly the same thing. It's just sometimes mathematicians independently come up with names for things, and then we have more than one name that's kind of standard. So this is one of these circumstances. Okay, so f is injective, or another word for that is one-to-one. If we have that, here we go. So we have that f of s1 does not equal f of s2, right? Whenever we have, or this is, right, so we like this looks like an A, so that's and that's for all. So an A is in, right, that's how you can remember that. Okay, so S1 and S2 in S satisfying right, so if I have two elements that are not equal to each other, then these had better not be equal to each other. So distinct elements go distinct places. Okay, so here's kind of my no picture. Okay, so I have an S here. I have two distinct elements, S1 and S2. And for whatever reason, they want to go to the same place. Maybe it's really nice, like a beach. Okay, so we would have f. So we want to have that f of s1 equals f of s2. Okay. Or rather, we don't want to have this because we would really like for this to be injective, and we spoil it when we send two things to the same place. Okay, so this is my no picture. Okay, we don't do this. We don't send two things to the same place. No, not injective. Okay, so this is no, we don't want to do that. Okay, because for injectivity, need that no two elements of S go to the same place. Okay, and in our problem in particular here is that S1 and S2 went to the same place. Okay, so the problem was that S1 and S2 went to the same place. funny way to write this, that it's like a no definition. And we can kind of turn this around, and the way that we're going to turn around is going to make it much more useful for proving that something satisfies injectivity. Okay, so here's an equivalent injectivity definition. Right, what does it mean for two definitions to be equivalent? It means that a function satisfies one if and only if it satisfies the other. Okay, and this one is useful for proofs. Ready to say, here we go. So we're going to take, so we have that f of S1, right? If this equals f of S2, then this implies, right, if you're not familiar with this symbol, this is the implies symbol. Right? And it implies that S1 equals S2, and I'm actually gonna I'm gonna put this up here, which is a little different than how I did it in my notes, but I generally like for this to be in the beginning because it has less confusion somehow, that for all S1 and S2 and S, we have that if this is true, then that is true. Okay? Right. So, how do we prove that F is injective? Well, first, right, so this is an implies proof, so I assume this side and I show that side. Okay? So I assume f of S1 equals f of S2, and then I show, assume, I need to assume that f of S1 equals f of S2, and then I just show that S1 equals S2. Okay? Then in different cases you show it in different ways, but this is how you do it. And I want to give a warning. This is definitely worth talking about because, as I said before, this is something that students often confuse. And I learned this from one students told me here they learned this from one of the professors here, Professor Chalrosi, who likes to do that apparently. So, but I like it, so I'll do it too. That's my warning symbol. So people often confuse this. Right, with a well-defined definition, okay, where we have that so in this case we have that S1 equals S2 implies that f of S1 equals f of S2. Okay, so what's the difference between these? If you look at them, my implication is in the opposite direction. Here, I assume that these are equal, and then I need that these are equal. Okay, so if this is true, then this is true. And then we go in the other direction, right? If this is true, then that is true. And those are different. And that's an important thing to know, that implications don't kind of, they're not interchangeable, okay? So the direction of implication is switched. Okay, and the difference is that between, as I think I mentioned in one of these videos, between the horizontal and vertical line tests. Okay, the difference is that the horizontal line test for injectivity right, like this, so I have alright, you've probably seen this before. What's the problem here? Oh man, I hit the same F value for two different, right, so this is S1 and S2, these are different values here, right, they're supposing this is S, right, but I get that F of S1 equals F of S2, right? So here I have F of S1 equals F of S2, and that's a fail, right? Because we have that, right, S1 does not equal S2, but those are the same. So that's how we'd fail injectivity, but this is different than if I took, so this is for injectivity, and the vertical line test for being a function. Okay, so I have here right, that I have I have that these are distinct, right? But they come from the same S1 value. So S1 equals S2, but these are actually distinct. Okay, so this is a fail here. Okay, so I hope that makes a little sense, so that now we can move on to surjectivity. So don't confuse being injective with being well-defined. Draw some pictures for yourself if you're getting a little confused. I find that's often helpful. So here's the next definition, and we're still under this assumption that f is a function from s to t. Okay, so we say that f is surjective, or another word for this is onto, just like in the other circumstance. They're just two different words for the same thing. That's okay. For each t and t, I'm going to use another logic symbol here. Right, the upside down A is for all, and this is a backwards E, and so this is there exists. Okay, so for each element of T, we know that there's going to exist an element S and S such that f of s equals t. Okay, so again we're going to do a no picture. Okay, so we're going to have our s over here. Okay, and I'm going to have, actually I'm going to add in another one here. It's a little different than the notes, but I think shouldn't be too much of a problem. Our green tea, always delicious. And so here I have some points here. Maybe I'm going to call these T1, T2, and T3. And maybe my function f sends, right, so maybe it sends both of these here, and then it sends this one here, and then we have a problem, right? And what is my problem? So this is, no, this is a horrible circumstance. Why is this such a horrible circumstance that f would do such a thing to us? It's not surjective because it left this poor guy all on its own. Nothing went there, okay? So, for surjectivity, so we need for surjectivity that there are no lonely T and T with nothing mapped to them. Okay, so there's my problem element there, right? Nothing is mapped to him, so he's very sad and lonely. Okay. So that's why this is a no picture, is because there's something in my codomain that isn't hit. Okay? So in other words, okay, so in order for f to be surjective, okay, so it must hit every value in t. Okay? No lonely elements sitting in T without anything going to them. We don't do that in surjectivity. Okay, so how do you prove surjectivity? We talked about how you prove injectivity. So how do you prove surjectivity? Okay, and I'm just going to emphasize that this is a for all there exists proof. It's good to know. You can kind of categorize these. So what I'm telling you is really the kind of thing of how do you do a for all there exists proof. Well, the for all part tells me that I let T in T be arbitrary, because this has to be true for all T and T, so I'm going to let T and T be arbitrary so that I'm proving it for all T at once. Okay? And then I need to find so I need to find an S and S such that f of s equals t. Okay, so I want that to equal t. But I do the finding in my scratch work. Okay, so I'm going to kind of note here the find. The actual process of finding it, this should happen in your scratch work. You don't actually write that part out in the proof, okay? But the part that we definitely write out in the proof is that you show that it satisfies what it's supposed to, which is that we show that f of s equals t. Okay. And then one last definition. where we still have that f is a function from s to t, is that we have bijective function. So definition 3. Okay, so we write, so f is bijective. If and only if we have that f is both injective and surjective. Okay, so it has to satisfy both of these. So let's look at some examples. So these are examples for injectivity, surjectivity, and bijectivity. Okay, so let's look at the function 1. So we're going to have f is going to go from z to z, where I have x goes to x squared. Okay, this is fine. This is a function. My outputs are in z. I'm happy, but this is not injective. So why is this not injective? The problem is that I have that f of 1 equals f of minus 1. Okay, so 1 and minus 1 give me the same output, but 1 did not equal minus 1. And this is basically exactly that picture I was showing you earlier of the horizontal line test failing. Okay, and then it's not surjective also, right, because we have lonely elements. Okay, so if I look at the image like this, okay, then this consists of non-negative integers only. Right, so in particular, I have this, so f of z, right, does not equal z. Okay, that's another way to kind of say surjectivity is that the codomain and the range are exactly the same. Okay, that would be another way to talk about surjectivity, and these are not in this circumstance. Okay, so i.e. the codomain and range are not the same. Okay, but here's kind of a magical thing. Okay, changing the domain or codomain can change this, so it can change our fate in life. But changing the domain or codomain can change whether a function's right, whether it's injective or surjective. Okay, so let's kind of show this. Onward bound. So let's look at how do I make this injective? Well, I have to get rid of, right, so this picture looks like, okay, so I start 0, right, and then 1, 1, and then I'm squaring 2, so I should get like 1, 2, 3, 4. So looking at this picture, and let's make that blue, this is kind of the output. You can kind of see how to make sure, right, so I run into these problems because 1 and negative 1 go to the same place, right? I fail the horizontal line test. 2 and negative 2 go to the same place. I fail the horizontal line test. Well, what if I just got rid of all of everything on that side? Oh, then I'm good. Okay. So if I take 2, so if I go to send, so G goes from N, so I've changed the domain here, but I kept the same kind of description of the function here. X still goes to x squared. This is injective. Okay, so now if G of x equals G of y, right, with x, y being natural numbers, then we know that x squared equals y squared, and x and y are greater than 0, so I know that x equals y. Okay. And now, so I'm injective, right? I needed that if I started out with having these be the same in my domain, then the inputs must have been the same. But the only way for these to have the same square is if they're plus or minus each other. But I assume that both of them are positive, so that told me that x equals y. Okay? But unfortunately, it's still not surjective. Right, since, right, if I apply, oops, I want to have a G here. And an N. There we go. Fix typos on the fly. Okay, contains no negative integers. Right? But the codomain Z does. Okay? So, in the next stage, we just replace the codomain with the image. So, here we go. We can make G surjective by replacing the codomain with the image. Right, so here we go. So we just write it like this. So we say H goes from N to the set of all x squared such that x is a natural number. Okay, I'm just replacing with its image. I still send x to x squared, and now I'm happy because now it's bijective. Right? So I'm going to summarize over here, okay? Or I'll summarize verbally, which is that if I have a function, right, I can make it, this one's not injective because two elements are sent to the same place, but they're distinct elements, okay? It's not surjective because the codomain and the range don't match up. So how do we make it injective? We just make sure that anytime you have some elements going to the same place, you only include one of them in the domain. So we changed our domain. If I wanted to make it surjective, then all I need to do is just replace the codomain with the range. It sounds like cheating, but it's great because then you have a bijective function. Okay, so that's it, and I hope again that this was helpful and that, try to do some of the problems that are in the, I put a variety of problems as well as solutions so that hopefully you can get the hang of how all these things work and that you will watch more videos in the future.